This video will cover the topic of DFA minimization, specifically focusing on the Myhill-Nerode Theorem and related algorithms. It explains the concept of reducing deterministic finite automata, or DFAs, to their minimal equivalent form, while ensuring that the language recognition capability is preserved. Let's define DFA minimization. It is the process of finding the DFA with the minimum number of states that accepts the same language. The goal of DFA minimization is to remove redundant states while preserving the DFA's ability to correctly recognize the language it was designed for. This ensures that the minimized DFA operates efficiently and accurately. A key concept in DFA minimization is that of equivalent states. Two states are considered equivalent if they produce identical behavior for all possible input strings. More formally, states P and Q are equivalent if for all input strings W belonging to sigma star, the transition from state P on input W leads to a final state, if and only if the transition from state Q on input W also leads to a final state. The Myhill-Nerode Theorem is fundamental to DFA minimization. It states that a language L is regular if and only if it has a finite index under the Myhill-Nerode equivalence relation. In simpler terms, the minimum DFA for a regular language has exactly as many states as there are equivalence classes induced by the Myhill-Nerode relation. The table filling algorithm is a bottom-up approach used for DFA minimization. This algorithm identifies pairs of states as distinguishable if they can be separated by some input string. The algorithm operates in two main steps. Step 1 involves marking pairs of states where one is a final state, and the other is a non-final state. Step 2 involves iteratively marking pairs of states that have different transitions on the same input symbol. Here is a snippet of code to implement the table filling algorithm. The minimize DFA function takes the set of states, the transition function, and the set of final states as input. First, a distinguishability table is created. Then, initial pairs of final and non-final states are marked. Finally, the algorithm iteratively marks distinguishable pairs based on their transitions. Another algorithm for DFA minimization is the Partition Refinement Algorithm. This is a top-down approach. It starts with an initial partition consisting of two groups, final states and non-final states, and then refines this partition until no further splits are possible. Partition refinement is more efficient than the table filling algorithm, with a time complexity of order n log n, where n is the number of states. DFA minimization offers several key benefits and has numerous real-world applications. Some of the benefits include memory optimization, faster state transitions, a simplified automaton structure, and a canonical representation of the DFA. DFA minimization is used in compiler design, lexical analysis, pattern matching, and hardware optimization. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.